Thanks, and thank you for the invitation. It's great to be back at NARA. I'm going to talk about these three-dimensional topological defects in 3 dimensions that we saw experimentally, and then give a little bit of a way towards maybe vortex knots, how you can create, or how that vortex knots should exist in these ordered materials or matter. But I want to thank my research group, of course, who have helped me on the way to get here, and especially my collaborators, David Hall and Toni Annala. And you can also see from the list that I have a lot of Japanese collaborators here on these topological things, especially Mikko Nakahara, who lived here in Nara, and I visited Mikko many times here back in the day to work on these Bose gases. Most of my research is actually not done on these Bose condensates anymore, but we mostly work on superconducting circuits, and we even spun out a company IQM about 5 years ago from our lab, and it's quite now successful in building and selling quantum computers. Our lab looks like this. You can see that there are 4 diluted refrigerators very closely packed, and I quite often joke that this is the highest density of diluted refrigerators in the world. It's not the most of them, but we have 4 very, very close to each other. All right, but I'm not going to talk about these in my talk today. I just wanted to tell you that where I come from. I'm instead going to tell you how we are giving you or the world. I like this picture because it's kind of shows that we are giving you monopoles, for example, in these quantum fields or knots or skyrmions. And then we also saw how, from these more elementary topological defects, you can go to more structured defects like a ring shape, an Alice ring that is made out of a monopole. And then theoretically, we are proving that in this matter, you can have these topologically protected vortex links or even knots. All right. Before I talk about the experiments, I'd just like to also highlight that it's, of course, thanks to David, who has been able to build this machine that is, really, really, really nice for these experiments. And he's really a great scientist. I learned a lot from him. And here in the photo, you can also see Mike, who was back in the day a postdoc in David's group, and he was together with David making these monopoles. Here in the front, you see the experimental apparatus that looks more closely like this. And how it works is that, there is another sort of chamber where you load atoms here, very cold atoms, you laser cool them further, and I think you laser cool them earlier, but here you do evaporative cooling, and you will really make the atoms, rubidium atoms, to condense into the sort of the macroscopic ground state of the system called a Bose-Einstein condensate. And that is a quantum sort of system where you can kind of think these atoms that they move, that there's a one giant wave function sort of telling you how the atoms move. And there's also, of course, the internal degree of freedom as well, which we will come to. It turned out that this machine that David had built was exactly what we wanted. So with my PhD student, Ville, we proposed a way to create these Dirac monopoles in these Bose-Einstein condensates. And we didn't know about David's machine back then, but then, then we learned that he has, this is from David's this picture. It's showing these magnetic field coils, and with these quadrupolar coils here, you can create this kind of magnetic field that has that sort of 3-dimensional shape. And with the other coils, you can move around the 0 point of the field. Turns out that there is topological winding in the direction of the field. So we don't know how to create a monopole in a field, a magnetic monopole, of course. We don't know how to do that. But it turns out that this has the topology of a monopole if you look at the direction. And that's exactly the reason why we would then create these monopoles in the BC order. And you can basically in real time you can shift around this zero of the field. You can do it adiabatically so that the field follows, and that's how you can create, for example, the original Dirac monopole that we proposed here. Or you can do it instantaneously, and then basically you are starting to do local rotations to your order given by the field direction, and that's a different way of doing defects. I will show what that creates. And you can choose your initial state. You can, for example, choose either polar or ferromagnetic state where you start from. And this is a little slide telling you what's the difference. So it's a spin one quantum field, and spin one can be, for example, in a ferromagnetic phase where the sort of the length of the average spin is maximized, and in that phase, the order parameter space is basically SO3. So it's basically this triad that has a direction for the spin, but there's also like a twist angle about the spin. So that's the topology of it. And then you can calculate the different homotopy groups mathematically. And so there are two kinds of vortices. There is no monopoles. There are some three-dimensional defects. The polar phase is different. Basically, the average length of the spin vanishes. So, but then there is this sort of nematic order that tells us that along which direction, in a way, it vanished. The spin is zero. So there is still like a coordinate axis associated with this sort of order. And it turns out that the order parameter space is then basically this director times a phase. There's going to still be a quantum phase for the particles, and then there's this twofold symmetry you take out. And then the topology becomes even richer. So you can have topological monopoles now in that system. And how it turns out is that when we first started from the ferromagnetic phase and we did the adiabatic ramp, and then we created this kind of Dirac monopole or an analog of Dirac monopole. Depends on how you define Dirac monopole. And then when you started from but that's not a topological monopole. There is no, because pi2 was 0. But then if you started from the polar phase, we created this topological monopole in the system. And then we went to an instantaneous sweep, and then instead of a monopole, we created a quantum knot or a Hopfian. And then we went to the ferromagnetic phase, we did the same thing, instantaneous sweep, and we created 3D skyrmion. And here is a little sort of slide that tries to tell you the differences of the structures of these systems. So the Dirac monopole has the spin that is winding in this sort of three-dimensional way, but then because of the local Berry phase, the Berry phase arises because of the triad is basically, it has to wind also about the spin direction. You will then have a 4 pi phase winding somewhere that terminates at the monopole. So there's basically a vortex that ends at this point. So there is no pi2 winding, strictly speaking. But then in the polar phase, there is no Berry phase because the order is different. So you don't have this sort of vortex that ends. You have a pure topological monopole in a center. The quantum knot basically realizes that the Hopf map, and I will describe later on how that looks like. But basically, you get these sort of 3 images of different directions of the director, and they form these linked rings. And that's a beautiful experiment as well. And then basically the skyrmion is the Hopf map added with the phase again. So you get now the phase from the twist angle again about the spin direction. So along each of these loops that you have here, also the phase is changing. And that's why instead of this Hopfian, we set it in 3D skyrmion. So basically, you cover the full order parameter space only a number of times, discrete number of times, whereas in here there is, infinitely many times. All right. So let me now make a little summary of this, like why we think this was great. Let's take a vortex in 3D. It looks like a line. In 2D, it looks like a monopole, basically a single, or it looks like a point. It's a point defect in 2D. So if you want to have a singular vortex, you need at least 2 dimensions. This is why the table tells you this. In 1D, if you go around the vortex, it looks like a non-singular solid. It's the same defect, basically. You just look at it in 3D, 2D, or 1D. So then in 1D, it becomes non-singular. For monopoles, you need at least, like monopoles, and I talk about monopoles, you need at least 3 dimensions to see the monopole. If you look only at the surface of the sphere, it looks like a 2D skyrmion. Now, the nodal and the 3D skyrmion, we would need 4 dimensions to see them as point charges. I don't know how to do that, but we do see these kind of point charges now in 3D, but they become non-singular. So all of these are kind of related defects, and you know that vortices have been discovered very, very early on experimentally. And in these quantum fields, I think we were the first ones to see monopoles in general, or nodes, or 3D skyrmions. Of course, in these liquid crystals that are classical fields, you know that, and other classical fields as well, some of these have been seen even earlier than us, and you know better than me the liquid crystal research. Okay, let's have a peek at the Dirac monopole case. And why I like this work so much is that we actually did realize Dirac's theory. We didn't realize it with electrons and real magnetic monopoles, but instead we realized with the spin degree of freedom acting as a synthetic magnetic field. So what Dirac worked out, he must say that even if you have a single magnetic monopole, then you would have this sort of phase accumulated to the electron wave function, and you need to have a nodal line where the electron particle density goes to 0, and that nodal line ends at the monopole. And if you do have even a single magnetic monopole in the universe, all charge becomes quantized. Electric charge becomes quantized. And we know that electric charge in the observation has been quantized, so it would be really, really great to be seeing these real magnetic monopoles, which have not been seen yet. Instead, we now put this spin degree of freedom in this 3-dimensional shape, and locally it kind of creates a vector potential or flux, magnetic flux through the surface in the same way as a magnetic monopole would create for the electron. Now, if you look at the scalar degrees of freedom, this is the exact analog of the electron wave function that Dirac was talking about here almost 90 years ago. And in experiment, we do see, so these are now experimental images where the color represents the direction or the magnetic sort of degree of freedom, and the intensity tells you the particle density in that sort of component. And you can see that we do see a nodal line here that ends at the center. It's the same picture that we get from the simulation. So we have created this kind of synthetic field that has a magnetic monopole in it, but it's not, it's not a real magnetic monopole. It's not in the real actual electromagnetic field. But we have realized this Dirac's sort of idea. And we do also see the nodal line to split into 2. So it has a 4-pi winding, and we can see that it can split into 2 single 2-pi windings. So it is not just an artifact of of our experiment. All right, let's look at the topological monopole then. Here is what you would expect from the theory. So this D is now the director of the field, and very easily you will see that okay, it should start to look something like this. That on the z-axis you should have the z component, which is the blue one, and then you should have the x and y components near the hemisphere and or near the equator, and they are kind of split here now because of the way we do the imaging of the cloud. But you will see that the simulation and the experiment again matches very well, and you know, this kind of shapes when you see them in the experiment in the zero component. This is the z component that you should see here on the side. They tell you that okay, everything's good. I have the monopole done, and it's in the plus and minus one components, you can see that you should have in principle like winding of the phase. So you should kind of see these vortices in a way in these two components. The density holes, we do see them in the experiment, and but they are not really real. They're not like vortex defects, because it's a single monopole defect that we have. Them. These vortices just appear in the individual components if you separate them. And actually we can do a projection. So this is in the z projection. When we project the 90 degrees of freedom in the z direction, we have the z component here in the zero sublevel, but we can rotate the projection direction, and we actually do see that these vortices counter-rotate with our projection direction. So again, they are not artifacts of the system. They're not really actual vortices. They are phase singularities only in individual components because they are part of the monopole. Okay, and then my PhD student went actually to work with David for a while to Amherst, and he did some experiments where he first created the monopole defect, the isolated monopole, and then was seeing that it does decay in time into the Dirac monopole scenario. So this was a nice experiment, and here we did see like a spontaneous appearance of the nodal line. So we had first no nodal line in the system, but then depending on where we created the topological monopole and weighted, the nodal line appears. Either if the nodal line wants to minimize its length in a way that if we create the topological defect, the monopole here, we see a nodal line appearing like this. If we create it down here, the nodal line appears like this. This is really an emergence of the nodal line from the fact that the system wants to minimize its energy. Okay, then about the quantum knot or the Hopfian, that we create now by instantaneously changing the magnetic field zero from up here into the center, and then we start to create this position-dependent rotation of the system, as I mentioned. And the end result is this. So if you look at the direction to this sort of in this direction for the director, the pre-image of this. So in the real space, we would basically map this direction into this ring. And then if you take different directions opposite of each other, they create these linked rings. And what is great about the experiment is that we can now, for example, if we project into z direction in the zero component, we look from the side, we now see the sort of the up and down directions. So we see the core, we call this the core, and then we see the boundary now. In the z component, the up and down, they correspond to the boundary and the core here. However, now if we take a projection along x or y, we should see this kind of linked rings, and that's exactly what we see. You can see when you look from the top, you can see two rings, and from the side it looks like an X. And this is what I like about the experiment. When we directly on the experimental image see these sort of linked rings, and that was really like when we saw this the first time and realized that we actually do see these rings right away from the experiment without actually even simulations, we were really amazed. But of course, the simulations also tend to give us the result. We made even a nice video, like when you start to tie up this knot, and so the system is so stable that we can actually make a video out of it. But I don't have time to show it, but you can take a look. And as I said, the skyrmion is basically the same as a quantum knot, but along this ring, you will have the twisting of this order parameter. And we call it the 3D skyrmion or the Sankar-Volovich skyrmion, but maybe we should just call it the skyrmion, because later I learned that actually skyrmion was considering in his original work exactly order parameter space that we have here, and exactly the same thing. So maybe this is the skyrmion, not the 3D skyrmion. Okay, but anyways, the theory and the experiments they do now also match. There is little difference now somehow in the experiment if you compare to the theory in the trap. But then once you do the expansion of the thing, then the theory and the experiment match well. So we also made the skyrmion. What is nice about the skyrmion is that this synthetic electromagnetic field is very versatile. It has magnetic field, electric field, non-zero magnetic charge, electric charge and current density. And actually this sort of, again, you get the Hopf map from here. And one sort of theory for ball lightning actually has this topology and has this structure in its magnetic field, electromagnetic field. And that's why it was in the news said that it might be a quantum ball lightning or whatever. But maybe the ball lightning is not really this kind of structure, but at least according to one sort of proposal it was. Okay, now I have not so much time anymore. I try to very quickly tell you now about the sort of the Alice rings and the vortex knots. So the Alice ring is basically has far away the same topology as a monopole, but like David was talking about the splitting of the vortex, now it's the splitting of the monopole into a vortex ring. And so locally you can deform the monopole into this kind of vortex ring when you have this nematic order here. And you can see that the sort of the direction of the D vector is flipping when you go across, but that flip can be then compensated by a phase flip of pi in the order parameter. So there's no discontinuity in the actual order parameter when you go through the ring. But however, the direction of the field, in a way, direction of the director actually flips. So in some sense, if you put a monopole through this ring, the charge is flipped. So if you have a +1 and -1, they basically switch charges when it goes through. And with Tony, we did this sort of map here, and we were able to kind of, even in a more general case, mathematically describe how that charge conjugation happens, and what is actually the charge ambiguity of these monopoles. Basically, you can't say whether one monopole is plus or minus, but you always have to compare different monopoles to the charges of different of these entities. And yeah, this is the more general case, not just sort of plus minus ones, but there can be some more complicated group related to it. All right, but the experiment again shows the Alice ring. It looks pretty much so. This is the topological monopole, and then when you wait for a while, you actually it will deform into an Alice ring. And I don't have time to go to the details. But instead, I want to use this last 2 minutes to describe you the vortex knots and links. So it turns out that a subgroup of the spin 2BC cyclic phase is the quaternion group. And it can also be realized in biaxial nematic liquid crystals. And for that sort of order, you can create this so-called non-Abelian vortices. So it means that this order is rotating about a certain axis when you go around the vortex. And these vortices, they have directions and they're non-trivial rotations. And it turns out that these Wittinger relations now tell us that if these two vortices cross, well, they don't really cross, but they kind of go like this. So when you look from here, then the direction of one vortex should change, or the nature of one vortex should change when it goes under the other, according to the Wittinger relations. So this is basically what happens if one vortex goes under this one, it switches sign. And it turns out that all topological, all knots and all non-trivial topological defects or this sort of topologies of these vortex tangles, they basically can be reduced into these very simple structures or bunch of them. And for example, Borromean rings, as you can see. But so basically no knots are topologically protected in this system. Only these linked structures. But then we went ahead and we went to this binary tetrahedral group that actually is sort of extension of what we were describing earlier, and that can be also realized in this cyclic phase of spin 2 BEC or this vent nematic liquid crystal. And then we found that in this experimentally realizable system, we do have topologically protected knots. The trefoil or the figure 8 knot are protected, so they are potentially experimentally realizable. There's also the Solomon link, which you can kind of create from these knots, if you like, with topologically allowed deformations. All right, so I think I ran out of time, so I described about making the monopoles, Alice rings, theory of these knots and links, and sometimes when you get the papers published, we pop a champagne, and here you can see some of the authors that I talked about. So thanks for your attention, and I still have time for a few questions.